Okay, so number 35. Here's the equation, the balanced equation, and they give you enthalpy. Yeah, so 35. Part A, you have 4 moles of iron. It's reacted with excess O2. So that part's just irrelevant. You have 4 moles of iron, and you have 4 moles of iron and 102 kilojoules. Yeah. So basically, for every 4 moles of iron, this this amount of energy is produced, or in this case, heat, energy in the form of heat, and this becomes negative 1652 kilojoules. The book says 1650, which is kind of, I don't know, that puzzles me as to how they got that, but this is basically the process. B, yeah, you just do the same process. Fe, Fe2O3. Same process, 2 moles of this. They're the same product, if you didn't know. I mean, same product, if you didn't know. And this was negative 1652 kilojoules. And the answer becomes negative 826 kilojoules. Part C, how much heat is released when 10 grams. Okay, it's basically the same problem, except instead you have to change the 1 gram of iron into moles before you can do all that stuff. So the conversion is 1 mole over 555.85 grams of Fe. And then you do it again. That is 4 over negative 1652 kilojoules moles. And then cancel out, cancel out, cancel out, cancel out. You end up with negative 7.39 kilojoules. Or whatever the book says. This is what I got. D. How much is released when 10 grams of Fe? Oh, okay. So this is a different problem. This is a limiting reactant problem. So you find the limiting reactant, 10 grams of Fe times 1 mole of Fe over 55.85 grams Fe times to find the limiting reactant, I just convert both of these into the product. So mole conversions into that product. What was it? 4 moles over 2 moles. And this 2 moles is the Fe2O3, if you couldn't see from the balanced equation. It becomes 0.08 moles Fe2O3. And you do the same thing for oxygen. 2 grams, right? Yeah, 2 grams of O2. You multiply by 1 mole. Yeah, I'm not going to write the O2s and stuff because that's really tedious. That's 32. That's a bad 3. 32 grams times 2 moles over 3 moles. And this is, of course, the product. And this is 0.04166. 66 moles. Which one's lower? This one. That's the limiting reactant. O2 is the limiting reactant. So you just use that. Use the yeah. You just use that amount of moles. And there was two moles. Yeah, you have to do it again for the negative 1652 kilojoules. Yep. And you get 34.4 kilojoules. Is that negative in the back? Let me see. 35. Yeah, it's negative. It's now 37. Ooh. Assume that all heat in sample exercise 6.3 comes from combustion or propane. What mass of propane must be burned to furnish this amount of energy? I'm assuming the heat transfer process is 60% efficient. Okay, so this is actually a very easy problem too. It just sounds kind of confusing. So balanced equation, delta H equals negative 2221 kilojoules. Yeah, Q would be equal to 1.3 times 10 to the 8 joules. Yeah, sorry. I was spending that time flipping my book to sample exercise 6.3. You should look at it too. So this is of course the 60%. This is of course the 60% yield of the actual one. So you need to convert this back into 100%. So you just do this. Is equal to 0.6 times x. So this is basically saying that 60% of the actual yield is equal to this, and you just divide by 0.6. And then the 100% efficiency would give you a 2.2 times 10 to the 8th joules. And then from that, you're supposed to find the mass of propane must be burned to furnish this. Okay, so you just do 1 mole of C3H8 over 2.2 times 10 to the 6th. Okay, yeah. So, if you didn't know, this comes from the delta H. This is just converted into joules of the delta H. So from this, you can just obtain the grams of propane. And this, oh yeah, if you don't understand why this actually happens, it's basically because delta H explains the transfer of like energy through the entire balanced equation. So 1 mole of this results in this enthalpy change. That's basically what this conversion is saying. So this is 44.09 grams and becomes 4,400 grams of C3H8. And that should be right in the back. Yes, it is. And apparently, connection's lost.